So how we can able to implement these multiplexers? So basically multiplexer is nothing but many to one. So it is in the order of 2 power n to n. So generally this 2 power n will be will be represented in terms of binary values. So 2 power n. So in order to select many to one, so any one input selection has to be done. So in order to do that, this multiplexer will be having a select lines. Okay, so based upon the select lines, we will be having the output will be clubbed to the input section. So this is a simple diagram what we are going to represent. It is a 4:1 mux. So this 4:1 mux, how we can represent is nothing but 2 power 2:1. So 2 power 2 is nothing but 4. So means what, there are two select lines are there that we call S0 and S1. So based upon the value of S0 and S1, the output will be clubbed from the input section. So you can see here when the select line which is 0 0, so the I0 will be selected, therefore output is equal to I0. So when the select line is 0 1, I1 will be selected. Similarly when the select line is 1 0, I2 will be selected, and similarly when the select line is 1 1, I3 will be selected. So this multiplexer plays an important role in the design of VLSI subsystem. So especially when we go for the scarcity adder, and also we studied about the ripple carry adder. So there also we are going to use this multiplexer in order to find out the sum and carry expressions. So the corresponding this multiplexer can be used or implemented by the use of the switch level transistor, that is the NMOS transistor. So the following diagram, it depicts about how we can do the that is a row and column combination of the switches. So based upon the activation of each switch, that is nothing but from S1, S1 bar, S0 and S0 bar. So the input will we can able to club to the output section. So the same NMOS structure can be implemented by the use of this transmission gate also, in order to have a stability over here. So this is the stick diagram of this multiplexer, that is a 4:1 multiplexer. And you can see here the complementary, that is by the use of this transmission gate, we have implemented this multiplexer, that is a switch level. It has been converted into stick diagram by the use of this CMOS technology. That is nothing but we have a PMOS transistor at the top, and we have a NMOS transistor. That is nothing but it has been a combination of pull-up transistor and a pull-down network. So this is how we can able to create the MOS layout of the multiplexer. Okay, so this is how the mask layout of 4:1 multiplexer we can able to see here. So the standard cell, it is of the size 7 lambda cross 14 lambda, whereas the entire 4:1 mux, it is all about 44 lambda is to 28 lambda. So the standard cell, it has been replicated into 4 times in terms of arrow and column, so that it can be converted, or it can be implemented for the 4:1 mux. So this is the mask layout which is related to your multiplex. Okay. So in the today's class, we will be studying one of the important implementation wise. Means you have a circuit diagram and everything is. Let's say I want to build an parity generator. So what is the fundamental steps you are going to do the parity generator is? So first you are going to see the relationship input and output relation you are going to see it. So what is a parity generator? A parity generator is nothing but, so the number of ones which are there in a given number. So based upon that, we can able to see that whether it is a even parity and a odd parity. So let us say we are designing an odd parity generator. So when you want to design an odd parity generator, so first you need to see, so what is the number of bits you are going to consider, whether you are going to consider for the 3-bit parity generator, whether you are going to consider for the 4-bit parity generator. So depending upon the input what we are going to select, so based upon that those many combinations of the input we need to analysis. So for the 3-bit parity generator, there will be 2 power, that is 2 power 3 input combinations will be there, that is starting with 0 0 0 to 1 1 1. So for all these cases, the output of the parity, that is the odd bit parity, we need to check it out. So for the each bit, so that is nothing but 0 0 0. So in this case, there is no ones is there, therefore the output is equal to 0. So in the case of 1 1 1, if the input section is 1 1 1 is having it, since it has an odd number of parity is there, odd number of ones are there, so therefore the odd parity output will be 1. So you are going to write the truth table. So based upon the truth table, you are going to do the K-map realization. You are going to do it for the 3-bit parity generator. So and you are going to do the simplification if there is any Boolean simplification is possible from the truth table. So after doing the simplification, what you are going to do is you are going to implement in terms of circuits. So you are going to go for the synthesis. After synthesis, that is a syntax checking, you go for the synthesis, that is nothing but RTL a schematic. You are going to do it. So once the RTL schematic is it has been generated, then you are able to see so what are the components which are required in order to generate this odd parity generators. So once you get to know that the components, so how the communication has to be established between the communication that is a component entities, you need to see it. So the implementation of your circuit diagram will be facilitated by this programmable logic arrays. So this programmable logic arrays is nothing but it is a combination of AND gate and OR gates in terms of row wise and column wise. So how you want and in which methodology you want to get the output, the desired output. So based upon that, we are going to use the arrays of your OR gates or the AND gates. Okay, so therefore programmable logic array, it is nothing but it is a fixed architecture logic which you can going to program. So means what, you can able to select so which how many number of OR gates you require in order to do the realization of the Boolean expression, how many number of AND gate you require in order to do the realization of the Boolean expression. So if you require a combination of AND gate and OR gate, means depending upon your Boolean expression, you can able to program so that directly you can able to implement a circuit by the use of these devices. So therefore, the programmable logic arrays are the fundamental entity or the tool which will allow us to create a circuit based upon the ANDing and ORing of the gate level logics. Okay, so this programmable logic arrays, it can be reconfigurable also. So means what, you have dumped one program and based upon that you have created a circuit, and after some time you want to dump one more program and you want to realize the circuit. Yes, it can be done. That is, the programmable logic arrays are reconfigurable digital circuits. So it's not that once you have implemented your circuit or once you have simulated your circuit, that circuit will be fixed for the entire duration of the lifespan. It is not that. It is reprogrammable. It is reprogrammable. Okay. So by the use of this programmable logic arrays, it is possible for us to create the circuit however you want to create in the for the realization of the Boolean program. So basically this PLL is nothing but it is an array of OR logics and logics. So what are the logic components you are going to have? So those logic component you are going to program it or you are going to fix it, and the connection between one logic program to another logic program, you are going to do it in terms of programming levels. So the programming level directly converted into circuit levels by the use of this programmable logic arrays. So you can see here this PLL architecture, you have a rows and columns as I said you. So you have a input variables, that is A, B, C, D, F is there, and A and A bar you have created. For the A and A bar you have combined the AND operation and you have combined the OR operation. So depending upon which operation you are going to use it, so that will be interconnected. That will be interconnected. You can see here. So P1 and Z1. So both, if you require P1 and Z1 means then this will be interconnected. If you require P2 and Z2 means then this will be interconnected. If you require Z3, that is nothing but P3 and Z3 will be interconnected. Now if you just want just a C bar, if you want just a C bar means then from this link you can able to connect your circuit and you can able to realize. Okay, so by the use of this programmable logic array, it will enable us to create the circuits for the realization of the Boolean expressions. So you can see here the programmable, different programmable what we can create is, for the Z1 is nothing but P1 plus P2 plus P3 plus P4 and P5, and we can create this Z1 by using the different combinations of this, that is nothing but A, B bar, C plus A bar, C bar. So if you want to represent, so we have created a stick diagram. So what are the stick diagram we have created? We have created a stick diagram for AND gate, we have created a stick diagram for the OR gate, and we have created a stick diagram for universal gate, that is nothing but NAND and OR. So the implementation of this NAND and OR can be realized or can be done from this programmable logic arrays. So means what? If you want to create a circuit for AB bar, that is nothing but NAND gate, means then what you require is you just require a bar of all the symbols, that is nothing but bar of all the symbols. So AB bar, how we can realize? By using a De Morgan's law, we can say that A bar plus B bar. So I will be taking one combination, that is A bar, and one more combination is B bar, and if I do the interconnection of that, then I will be getting a bar plus B bar. So you can able to program your Boolean expressions from this programmable logic array devices. So that is why it is called as a programming the array of AND and OR logic. So therefore the name is called as a programmable logic arrays. So we can design this programmable logic array is the one of the important question. Okay, so how we can design this? So we can design this by using a two important mechanism. One we call it as a product of sum, and one more we call it as a sum of product. So as I told you, if you want to design an AND gate, so what is the Boolean expression for the AND gate is A plus A into B bar, whole bar. So this A into B whole bar, it is nothing but it is a product of sum expressions what we can able to create it. So for this product of sum, we can able to use the sum of product. So since the AND gate, it is just one element, that is there are only two variables are there, that is but AB whole bar is there. So how we can do this? We can do the sum of product, two important we can do. How? 1 into A bar plus B bar into 1. So it is nothing but sum of product we will be getting. So from this sum of product, we can able to create or we can able to configure your AND logic and OR logic, so that we can able to realize A bar plus a B bar. So for that you can see here, this is the diagram what we can able to create for the this is the Boolean expression which we can able to realize for AB bar plus BC bar, or we can able to realize AB plus A bar B, or we can able to create AC bar plus DC bar, or we can able to create A bar B plus BC bar. Okay, so you see here the input section what we have. So we have A bar is there, and B bar is there, C bar is there, and these A bar and B bar we have connected to a AND and OR logic. So these are the OR logic and these are the AND logic. So you can see here the first one, A is connected and B is connected. Since it is a multiplied product, so therefore you will be getting AND one, that is AB you will be getting. And in the second case you can see here A is been connected and C bar has been connected. It is an ANDing logic, so there go you got a AC bar. And here the third one is and B bar is there. So you are connected or you are clubbed with this A, and B bar is there. From this B bar you have coupled it, so it has been given to an AND gate. And finally what you need is you need a BC bar is there, so you have it has been connected to B bar and C bar it has been connected. So from this you are using this ORing logic. So whatever the terminal you are going to OR it, so based upon that you will be getting a Boolean expression. So if you want to get a Boolean expression for this AB plus AC bar means, then you need to combine these two terms. If you want to get an Boolean expression, let's say AB plus AB bar, then you need to combine or you need to interconnect this horizontal line, that is the first horizontal line, and the third horizontal line you need to do the interconnection. Or if you want to have a AC bar realization, AC bar plus AB bar, if you want to do the realization means, then you need to do the interconnection of this AC bar plus AB bar. Okay, so this is how you can do the interconnection of ORing symbol, so that you will be realize the any form of Boolean expression by the use of this PLL logic arrays. Okay. So are you able to understanding this one?
Yes, sir.
Okay, so you can do, so it's not only these things we can able to realize all the complex realization of the Boolean expression by using these logics. Okay, so if you want to do the multiplication means, so let's say if you want to do the multiplication, let's say ABC, then what I should do is I should cross connect this link, I should cross connect this link, and I should cross connect this link. Or if you want to do the realization of, let's say, sum expression, what is the sum expression for the half adder? It is AB bar plus B bar A. So that we can do it how? AB bar means I can take this, and B bar I can take this. I can do the interconnection of this. You will be getting AB bar. And what you need is A bar B you need. So I can do the interconnection of this point. I can interconnection of this point. And if I do the ORing of those two means, then you will be getting a sum expression. Similarly, if you want to go for the carry expression means, so the sum adder half adder's carry expression is nothing but AB. So what is the AB? So just simply it is nothing but interconnection of A terminal and B terminal, and it has been given to the AND logic. So therefore you can realize this half adder. So similarly, if I connect same half adder, yes. Anyone? Yes, Abhishek, any doubts? Abhishek? Abhishek, any doubts?
No, sir.
Okay. So if you need a carry expression means, then what is the carry expression for the half adder? AB. So now if you want to go for the full adder, so how I can realize this full adder? It is nothing but the combination of two half adder, we got a full adder. So it is nothing but A exclusive with B exclusive with C. So if you want to go for the, as I was telling, the full adder means, then you need to combine the output of the one half adder should be given to the input of the another half adder. So that is nothing but A exclusive with B. If you do the exclusive with C means you will be getting a sum expression. And carry expression, what is nothing but? Carry expression is nothing but A exclusive with B multiplication with C. If you do that, then you will be getting a carry expression of the full adder. So that also you can able to realize by using this PLL method. Okay, so this is how we can able to realize that any form of Boolean expression can be realized by using this programmable logic arrays. And once you design your circuit, and okay, I have designed my circuit, and for the input section I am getting the output values. After that, I don't want to have this circuit. I want to create one more circuit. So what I can do is, yes, you can able to erase the existing circuit, whatever you have created for the full adder, and then you go and go for the new type of circuit also. So means what, if you want to realize another Boolean expression means, then you can do by reprogramming or by erasing the existing program which is on the PLL method. So therefore we call it as a erasable, means it is re-erasable programmable logic PLL architecture we are going to call it as. Okay, and this is the internal architecture how your PLL will look like. So you can see here the switches, horizontal rows you have and vertical rows you have. The horizontal rows we have connected to the input section, and the vertical rows we have connected to the VDD plus switches we have connected. So if you want to have a interconnection means, then through the use of switch, the vertical line and horizontal lines will be connected, so that it will be clubbed, and based upon the combination of your Boolean expression, either it will be ORing of the symbol will be taken, or the ANDing of the operation will be taken, depending upon your Boolean expression realization. So whatever may be the Boolean expression, it is possible for you to realize from this architecture of your PLL method. So now how you are going to do the floor planning of your PLL? So that also plays an important role. So the fundamental aim of our VLSI design is to have a compact IC. So when you want to create a miniature IC component means, then the floor planning of the IC also plays an important role. So this is the how we are going to place the component designs or the subsystem of the PLL architecture, or for the Boolean realization expression, whatever we are going to do it. So for that, this is the floor planning what we can able to create. So you can see here in the top portions we will be having the product rows, and in the right corner of that we will be having the sum expressions, and at the bottom case you can see here the inverting input resistors will be given, that is the V inputs. So through this V inputs only we will be giving the input section, and at the right corner, that is at the bottom, we will be taking the output section. And for both the inverting input resistors and the that is inverting output resistors, So two set of clock signals we will be triggering. So the two sets of clock signals we are going to call it as a phi 1 and phi 2. Okay, so based upon the triggering section of this inverting input resistors, so we can able to excite the number of p products, that is Boolean expression. Based upon that we can excite the product values, and also the sum values we can expect. So depending upon the combination of the sums, the output inverters will be stored, and the output the which is there in the output resistors, so that will can be taken from the output resistors. So this is how we can go for the floor planning of your PLL architecture for the Boolean expression realization. Okay. Shall we go for the next one?
Yes, sir.
So now you can see here the PLL, the dynamic logic diagram, means the dynamic logic whatever we have created in the earlier classes. So for that we can able to realize the dynamic logic array through the use of this PLL. So how this will look like the evaluation of your or implementation of dynamic CMOS logic by using this stick diagram. Okay, so as I told you, your dynamic logic will work in two mode. One we call it as a pre-charge mode, and one more we call it as a evaluation phase. So when the phi is equal to 0, it works on the pre-charge mode, and phi is equal to 0, it works on the evaluation phase. So in the implementation of this dynamic logic by using this 8 cross 4 cross 8 cross 4 PLL, we have used two different that is a clocking signal. One we call it as a phi 1, and one more we call it as a phi 2. Since in order to have a complement of that, so we have created phi 1 and phi 2 bar, and similarly phi 2 and phi 2 bar we have created. So if you see the transmission gate, so the realization of transmission gate, whatever the principles we have used, the same principle we are going to use in the case of dynamic logic realization also. So this is the diagram how we can able to implement or how we can able to realize the dynamic logic of your CMOS by using the PLL architecture. Okay.